We will look into the k-means clustering demo part, the practical coding implementation of it. So if you see, we'll try to understand the k-means as well. We already have a good overview of what k-means clustering algorithm is, but either way, I'll try to revise it and we'll try to understand more regarding the algorithm. So, what does K-means do? So, obviously, it's unsupervised learning algorithm, and it uses a clustering approach, right, to cluster the data into respective groups. And if you have unlabeled data, then you are going to use this, obviously. And the algorithm works iteratively to assign each data point to one of k groups. So we have to specify the k, and with respect to the k, it is assigning whatever the data samples that are present or the records that are present into these k different groups based on the features that are provided, right? And the data points are clustered based on feature similarity. So how we can check the feature similarity? So we are using some different kinds of distances, right? So we are obviously checking for the distance, and again, for calculating the distance there are different various type of distances, right? The way we measure, you have this Euclidean distance and Manhattan distance, and there are different types of distances. And in our three-dimensional space, basically we'll be measuring the Euclidean distance basically. And the results of the k-means clustering algorithm are the centroid of the k clusters, which can be used to label new data. So we are going to get the centroid, and with respect to the centroid, we are going to group the data into clusters, k clusters, and labels for training data. So yeah, so we'll be getting labels as well, in the sense like every data point is associated with a particular cluster. So if you see it, before k-means we have these kind of samples, and after k-means you have this samples clustered accordingly into three different clusters. So this is one cluster, this is one more cluster, and this is one more cluster. So this is how k-means clustering basically works. And yeah, so there are different applications of k-means. So there are a lot of applications. We can do this behavioral segmentation, in the sense like whatever the example we saw, like if a customer visits a store or a web platform or website, how we can segment users based on the purchase history, and also based on the different activities he performs in the website or platform, and based on the person's interests or the profiles that we have created by doing the monitoring. So we can do this behavioral segmentation, and there are some set of things like we can do inventory categorization, and also regarding the sensor measurements and detecting anomalies. So we can do all these different types of things using the k-means clustering algorithm. Sorry. Yeah. And yeah, regarding the working, so what we are going to do, so first we have to, it begins with choosing the number of k clusters. So we have to choose the k value, and again we'll see how do we choose the optimal k value. K signifies the number of clusters that the algorithm would find in the data set. Now choosing the right k is very important. So we have to choose the right k, and sometimes the k is clearly visible from the data when visualize it. So one thing is we can look into the data and try to identify the optimal k, or there are other techniques using, we can do this brute force kind of approach by trying different k values, and with respect to that also we can fix to a particular k value. However, most of the times this is not the case, and in a short time we'll see about how to choose the right k value. And yeah, the second step is to select k random points as centroids. So first what you'll do is, whatever, suppose in the example or previously you saw, you want to make this data into two different clusters. When you have to do it into two clusters, then we have to define these two different cluster centroids randomly somewhere. So the k points could be points from the data set or outside. So it can be data set points or it can be outside. And the random initialization of centroids that we are doing, it can sometimes cause random initialization trap. Yeah, so that we will discuss further. But basically, we have to randomly choose the clusters, and once you do that, then you have to assign each data point to the closest cluster. So you have these clusters, right? So you have these two different clusters here that we have grouped, and we have to assign the data to the respective clusters with respect to the distance between the centroid. So whatever the closest centroid is, suppose this is there, you will measure the distance between this centroid and this centroid, and obviously like this is less, right? So you are associating this particular point to this particular cluster. So this is how we are forming these clusters, and this is the initial step that we are doing. And again, with respect to the mean that we are calculating, so with respect to the points that we have, we will calculate the mean, and we will again reassign our cluster according to the mean. So whatever the mean value is there, we will take it as our cluster point, and we will define our new cluster, new centroid. So whatever the old centroid is there, from there we are shifting to this new centroid. We're shifting our position of the centroid to this new location, and we will do to the other cluster as well. We will do it similarly. And once you do that, again you will do the reassignment of all the data points. So once the cluster has changed, centroid has changed, right? So with respect to the centroid only, we are taking our data points, right? So now what we are doing is, with respect to the new centroid that we have formed, again we are going to find the distance between all the data points and whatever the closest points that are there with respect to the centroid. Suppose if you have this particular point, you are calculating the distance between these two centroids, and this is the closest one, so you are associating that particular data point to this particular cluster. So this is how we are doing the reassignment part. And yeah, so again we'll do the iterative sort of steps. Like first, what we have done, if you see, we have taken k number of clusters, and we have taken some random k points, and we have selected them as the centroids, and we have associated each data point to the closest centroid, and we have computed and placed the new centroid now, based on the mean value of the data points that we got. And yeah, now again we are redefining or reassigning the data points, right? So yeah, so we have done that, and we will do it iteratively. So again we will change our centroid, again we will calculate the data points and associate it to the centroid. So we will do it iteratively, so we will keep on changing our centroid position up to a point where there is no change in the centroid. So even after some set of iterations also, there is no change in the centroid position. Then we can conclude that the algorithm has converged, and we can stop our training part. So this is how we are going to get the clusters using the k-means clustering algorithm. And finally, if everything is good, then your model is ready. So this is how we are going to we are going to do in k-means clustering. And how to choose the right k. So to choose the right k, the condition that we have is, at the end of the day, what we have to do is we have to minimize this particular WCSS. WCSS is nothing but within cluster sum of squares. Within cluster sum of squares is nothing but whatever the distance between the data points on the cluster that is there. So this is the, suppose we have three clusters. Suppose if we have k equal to 3, then we have this centroid to points distance, right? Whatever the three clusters we have, and every cluster you have centroid and you have the respective points, and you are going to calculate the distance between individual points and the cluster, and you are going to sum all those distances, and you are going to get a distance here. So this is for cluster 1. Similarly, this is the distance for the cluster 2. Similarly, this is the distance for cluster 3. So we got this individual distances, and if you make a summation of it, and finally if you check it, you will get something called this within cluster sum of squares. And this should be minimum. So this is the metric that we are going to use to understand what will be the right k value. So you have taken k equal to 3, k equal to 4. You can try out different values and try to see the one which is giving you the minimum WCSS. So this is the metric that we are going to choose. And also, to choose the k value, there is something called elbow method, in the sense like, if you see, whatever the WCSS value that we have, and which is in the y-axis, and you have the number of clusters in the x-axis. So we want to find the optimal number of clusters, in the sense like, if you keep on increasing your k value, it doesn't make sense, right? Obviously it decreases your WCSS, but it is not that much significant. So if you see if you see the plot here, you can see that when k equal to 1, you can see that this is too high WCS, and if it is 2, it got significantly decreased, and 3, it got significantly decreased, and in 4, if you see the difference between 3 to 4, the difference between 3 to 4, it is not much. The decrease is not significant, and 4 to 5 also there is no significant difference. And similarly, if you, as you go move on further, increasing the number of k clusters, the k value, there is no much significant decrease in the WCS. So it happened only at k equal to 3. So we can conclude, or we can take, or it's a good idea that you pick your number of clusters as k equal to 3. So this is one intuitive method, which is a elbow method, using which you can choose optimal k value. So yeah, coming to the centroid random initialization trap, which we were discussing, right? So what happens is, suppose here you have initialized centroids in this way. So you have taken these 3 different centroids in this particular manner. So this is the initialization that you have done. And if you do it in this way, again you can see, right, you can see the difference between initialization 1 and initialization 2. So here the centroid is initialized, here one centroid, and here is second centroid, and here is the third centroid. But if you see it similarly, you can see that here is one centroid, and here is the second centroid. So you can observe the difference here, right? Obviously there's a difference. So if you do this different initializations, then there's a chance that your complete algorithm may go wrong, and there's a problem in the conversations, if convergence, if you don't have any reference, or if you are not doing the initialization properly, if you do it completely randomly, there's a problem. Whatever the centroid initializations that we are doing. So for doing that, there is something called this k-means plus plus initialization algorithm. Using that, generally we will initialize our centroids. And how this k-means plus plus algorithm works, everything is beyond our scope now. But basically, for initialization, we use something called this k-means plus plus algorithm. That is a famous one, or generally that we use. And we are going to look into this k-means clustering tutorial. So the same thing that we have discussed. So how the k-means algorithm will cluster the data points into the different groups. And yeah, habit does the steps. So whatever the 4 steps that we have discussed, if you see it intuitively, we can just check this. So first we have initialized our cluster centroids. So these are the 2 centroids, and then you have changed the position of your centroids, and with respect to the centroids, again you have done the reassignment part. So you can see the reassignment that has been done, and with respect to the reassignment, again your data points are assigned or segregated accordingly. So previously this data point was associated to red cluster, this red one, but now if you see, it has assigned to the yellow one. So you can see the difference, right, between this and this. So as your centroid changes, your data points that are associated to that particular cluster to which the centroid belongs to also changes. And as you see, finally you can see, right, so this is how the clustering has clusters have formed. So yeah, this is how the k-means clustering algorithm works, and this is the intuition of that. And again the elbow method that we have discussed. And as we implement, so here we are importing the set of libraries, and then we are ignoring the warnings part, and now we are loading the data. So this live.csv, I'll give you a feel of it. So if you see the shape of it, you have this 7050 rows and 16 features that you have. Basically you have only 14 features, but other 4 features, you have only 12 features, but other 4 features are nans itself. So we'll be dropping those 4 features moving further. And if you see, do a head of it to understand the data. Basically this data is regarding the statuses. So we have this different status id, and you have the type, status type, is it a video or photo, what is that? And it is a Facebook post data, actually Facebook status data, and what is the date when the status published, and what are the number of reactions that you got, number of comments, number of shares, number of likes, number of loves, number of wows. So we have all these different features here. And finally you can see these four columns are nans, right? So we have to drop them. And you can we can get the info regarding the summary of the data set. And we are trying to see is null. So is there are there any nans that are present in the data set, and you can see that this last four columns are complete nans, and we are going to drop them using this df drop dot df dot drop. We are dropping these last four columns, and again we are checking the info now. And we are trying to see the statistical summary of it of the data using the df.describe. So you can see the mean and standard deviation and the distribution of the data. And yeah, so we can check for the uniqueness of the status id, and you can see that they are obviously unique, right? Almost like all the statuses are unique status ids are unique. So obviously, like if it there like they are unique, so there is no much information that is present in the status id, right? So like we cannot group it according to the status id. With respect to the status published, also we are trying to see the length of it. And also they are almost so if you see the total number of the data set rows, they are like 7050. So it is 66,930 6913, which is also something closer enough, right? So there is no much correlation that is present with respect to the status published also. So if you see, we have status type. So we have this different status type. You have video, photo, link, and status. And if you see, you have only four things. So there's a good amount of correlation that exists with this status type, using which we can do the segregation or clustering part. So yeah, that's the reason we have dropped these two different features, status id and status published. Why? Because obviously, like, we are not going to use these two different features anyways, right? Why? Because we cannot use them for the clustering that we are doing. And again, we are checking the info part, whatever the features that are present with us. And again, we are doing a head of it to get a preview of the data. So now you can see the data. So you have status type, and you have this number of comments and reactions. So 1 2 3 4 5 6 7 8 9 10. So we have this 10 different features that are existing. And we have one non-numeric or categorical column, which is the status type, and other things are the numerical ones. So you can clearly see them, right? Now we are defining our feature vector and target variable. So status type is the target, and we are converting our variables into integers. So we are using something called a label encoder, which is a predefined method that is present in the sklearn pre-processing. So yeah, so we are doing a fit transform. So we are applying to the status type. So status type is a categorical one, right? So for categorical data, we have to use this label encoders to encode your data. So you can do one hot encoding or label encoding, so that you convert those categorical values into numerical format or binary format. Again, we can see the summary of it, of the data, and we can again preview it. Now you can see the status type, it got converted into numerical, right? So that is what we are trying to do. And now we will be doing the feature scaling. We'll be using a min-max scaler for doing the feature scaling part. So these things are obvious to you, right? As we have already discussed this set of things comprehensively. And then now what we are doing is we have this number of clusters that we have defined. The number of clusters are two that we have defined, and we are fitting the data accordingly, our x value. And you can see that we are initializing using k-means plus algorithm that I have told, and number of iterations are 300, and number of clusters are 2. So these are the different parameters. By default, k-means is going to take. And finally, you can see the cluster centers, which are the centroids for you. So these two will be the centroids. So we have a high dimensional space. It's a 10-dimensional space. With respect to that, we got these two different centers for the two different clusters. And yeah, so whatever the previous sum of squares cluster sum of squares concept that we have discussed, right? We have discussed that it should be minimum, right? So that is nothing but that is called inertia. Inertia is nothing but that within cluster sum of squares value, and we have to minimize the inertia. So that is what K-means clustering algorithm internally does. So it minimizes this inertia, and you can check the inertia as well. So we saw the centroids, right? These are the centroids, and yeah, so we are choosing our centroids in such a way that we are minimizing the inertia or within cluster sum of square criteria. And you can check the inertia as well. So it is 237.75 for k equal to 2. So this is for k equal to 2, and the less the model inertia, the better the model is. So that is a metric, and we can see that model inertia is very high. So this is not a good model. So whatever k equal to 2 that we have taken, right, so that is not the optimized k value that we can take. So there is some possibility of improvement that is possible here. And yeah. Yeah, so inertia is not a normalized metric. um, yeah, so the lower values of inertia are better and 0 is optimal. And in very high dimensional space, Euclidean distances tend to become inflated. So it would be difficult for us to calculate this inertia, and there is something called this curse of dimensionality that occurs in the high dimensional space. That is the reason we have to use some PCA kind of dimensionality reduction algorithm for reducing the dimension of our data, and then we can calculate our inertia. So in the pre-processing step, we can use PCA also, and after that we can use our k-means clustering algorithm. And yeah, so we can check here how many samples it has correctly classified, and what is the accuracy of that we are going to suppose that we are supposed to get, and y is the label that we have taken, and with respect to the y, we are evaluating our correct labels that it has predicted, and the accuracy is nothing but 0.01. We have taken the percentage, right? So you can see that it is 1% accuracy, which is very less. So obviously, like you have to improve the accuracy front, right? So now we are using the elbow method here, and we are trying to see how we are going to accuracy, how the accuracy is varying, and how even our inertia is varying with respect to the number of clusters. So you can see the elbow method here, right? So where the significant decrease is there. So up to the 4, there's a significant decrease that is possible. So we can try out k equal to 3 and k equal to 2. So we'll try all these different set of values. Again, we have used k equal to 2. Now we'll use different clusters. We use k equal to 3 here, and you can see accuracy is 2% again. Now we are using k equal to 4, and now you can see that accuracy has increased significantly. So you can see it is 62% accuracy. So whatever the accuracy that we got, and which is the highest one compared to the other clusters, right? So we have k equal to 2 and k equal to 3, and you got only 1% and 2% accuracy. But for k equal to 4, you got 62% accuracy, which is significantly higher than the previous k values. So finally, we can conclude that the optimal k value or the number of clusters is 4 for this particular problem. So this is how we have to do the k-means clustering part. This is the implementation of it, and this is how you will choose the optimal k value, and you will be using k-means plus plus algorithm for doing the centroid initialization part. So and inertia is nothing but the within cluster sum of squares value that we have to minimize. So that is what our goal is, finally, to minimize that, and we are choosing the k value also accordingly using the elbow method. By plotting it, we saw it visually, right? So at k equal to 4, it is significantly lesser. So we can increase the number of clusters also, but it will lead to overfitting part. So that is the reason we are not increasing it, and we are going to optimal one. So it is not too higher, or it is not too lower. It's a right choice of k, for which we get better results and better accuracy.